Hi, this is Dr. Perdue, and this is my entry for the MTT2K prize for the video commentary on a Khan Academy video. I had lots and lots to choose from, as you all well know, and so many different ways I could have gone in talking about this, but I chose the one on the sum of interior angles of a polygon. And I picked it because one of my primary issues with the Khan videos is not that they exist. I actually think that's great. All resources are useful and have a place. But what my problem is so many people, including, for example, Bill Gates, seem to be holding it up as the best example of teaching math. And with that, I vehemently disagree. So I'm going to start by just showing you his version of the sum of the sum of the exterior angles of a polygon, and then I'm going to give you what I think is a better way.
Several videos ago, I had a figure that looked something like this. I believe it was a pentagon or a hexagon. And what we had to do is figure out the sum of the particular exterior angles of the hexagon. So it would have been this angle, which we call A, this angle B, C, D, and E. And the way that we did it the last time, we said, well, A is going to be 180 degrees minus the interior angle that is supplementary to A. And then we did that for each of the angles, and then we figured out, we were able to algebraically manipulate it. We were able to figure out what the sum of the interior angles were, dividing it up into triangles, and then use that to figure out the exterior angles. And it was a bit of an involved process. What I want to show you in this video is there's actually a pretty simple and elegant way to figure out the sum of these particular exterior angles, I should say, of this polygon. And it actually works for any convex polygons when you're picking these particular these particular exterior angles, I should say. And so the way to think about it is you can just redraw the angles. So let's just draw each of them. So let me draw this angle right over here. We could call it angle A, or maybe the measure of this angle is A. Either way, let me draw it right over here. So this is going to be.
So while he's drawing, I'll just comment that it did bother me a little bit that he kept having this error about calling the angles external angles instead of exterior angles, and didn't even bother to re-record, his publication before he put it out there for all the world. I mean, I guess there's something to be said for doing it all in one take, but I kind of believe that, let's make it as good as possible before we put it out there for our students to look at. The other thing that bothers me a little bit about what he's doing right now is he keeps talking about drawing, not actually creating a congruent angle or constructing a congruent angle. And granted, the math, it's not that it's incorrect, it's just that it's not complete, and he's not explaining as well as I think it needs to be explained in order for someone to truly understand it. I mean, just look at this drawing. Is this something that makes sense to you? This is a place where he needs to go to a different tool. He needs to recognize that there are appropriate ways and tools and manipulatives to use when teaching these math concepts.
You could draw a line that is parallel to this right over here, and this right over here would be angle E, or you could draw it right over here. You would draw it right over here. And when you see it drawn this way, it's clear that when you add up the measure, this angle A, B, C, D, and E, you're going all the way around the circle. Either way, you could be going clockwise, or you could be going counterclockwise, but you're going all the way around the circle. And so the sum of these angles are just going to be, so A plus B plus C plus D plus E is just going to be 360 degrees. And this will actually work as...
And this bothers me too, because especially in geometry, notation is so critically important. A generally refers to a point in geometry, and an angle A is perfectly okay, but there's no angle symbols that he's used here. And we all know that you can't actually add an angle, you can add measures of angles because the measures are the actual values. So really here he should have the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D plus the measure of angle E is equal to 360 degrees, not A plus C plus D plus E, because that gives the students the impression that we're talking variables like in algebra. And even though they could be represented with variables in algebra, he doesn't have an algebraic let statement that says A is representing the measure of angle A in this diagram. And I know this may seem nitpicky to some of you, but those of you who are math educators, I know, agree with me because we've had these conversations before and we know how important the notation and the terminology is.
As I said, for any convex polygon, when I say convex polygon, I mean one that's not dented inwards, one that's kind of, so just to be clear what I'm talking about, it would work for any polygon that is kind of, that I don't want to say regular. Regular means it has the same sides and same angles, but it's not dented. So this is a convex polygon. This right here is a concave polygon. So let me draw it this way. So this right over here would be a concave polygon. I'm gonna draw it as a having the same number of sides. So I just kind of dented these two sides right over there in. Did I do that right? Let me see. Let me do the same number of sides. So I'm going to do that, that, and then that's the same side over there. Let me draw it like that, and then like that. This has 1, 2, 3, 4, 5, 6 sides. This has 1, 2, 3, 4, 5, 6 sides. This is concave. Sorry, this is convex. This is a convex polygon. This is a concave polygon. And the way I remember it is kind of caved inwards. And so what we just did would apply to any, if we're trying to find these particular exterior angles of any convex polygon. I apologize ahead of time if I've confused them all, because I have a feeling that I might have. This applies to any convex polygon. And so once again, if you take this angle and add it to this angle and add it to this angle, add it to this angle, add it to that angle, and add it to that angle. And I'm not implying that they're all going to be the same. I just drew it that way. I could show you that they are different angles. So I could say that one in green and that one in some other color. I think you get the idea. They can all be different, but if you shift the angles like this, you'll see that they just go around the circle. So once again, they'll just add up to 360 degrees.
Okay, so I have a couple of problems with the way he ended that as well. First, let's just talk about the definition of concave and convex. So you notice I've brought you over to a tool that I use a lot in my geometry class. It's a piece of software by Key Curriculum called the Geometer Sketchpad. And I'm just going to create a polygon here and talk about exactly what Mr. Kahn was trying to explain, which is the difference between concave and convex polygons. And while I appreciate his ability to describe something in lay terms, you know, for example, dented in or it makes a cave, that's fine, except it would also be good in addition to that to give the true geometry definition for the student, especially if these are supposed to be actual educational videos. And so probably what would have been the easiest thing is if he would have actually drawn in all the diagonals, and I'm not going to probably draw in them all, but I'll draw in, well, okay, I will draw in them all because I want it to be complete. Okay, and talked about, because it's not like this is a very complicated definition, you know, and to me this is no more complicated than explaining to the student dented or not dented. And the way it works is this: if all of the diagonals are located inside the polygon like they are right now, then the polygon is convex. If at any point there's a diagonal that lies outside of the polygon, then the polygon is concave. I mean, to me, that is really no more complicated than talking about denting or caves. Just to give the explicit definition, at least one of them. I mean, there are different ways that we could define these terms, of course, but give one that actually is valid mathematically and that can be used in a true geometry class. Because any geometry teacher, if a student is defining a term like concave and they say it's a figure that's dented, that is not going to earn them full points in terms of their response. It doesn't indicate the level of mathematical knowledge that we want. Okay, so that's one thing, the concave versus convex, and this is a tool where this is so much better than drawing by hand, which even though it's fancy and even though it's done on his computer and he can do it in colors, it's still the same thing as if we were to draw it on paper or draw it on the board. Why not use some actual technology to demonstrate this mathematics? And speaking of that, let me illustrate an even better way to show the exact illustration that he was trying to give of the exterior angles of a polygon. So here we have these angles measured dynamically, notice, because as I drag them around, the measurements affected all change. And now I can actually add up these measurements and show that no matter what I do, right, the sum stays the same. Now, of course, if the polygon becomes concave, as we just talked about, it does change the sum, okay? But notice what we have here. We have the ability to correct for that issue using the software. One more thing I'll show you, because I don't want to rant for too long, is that we can actually have an illustration here to show that these angles all sum to 360 degrees. And that's what happens here. So I'm going to click Shrink the Polygon. Just watch. Notice right here, perfectly illustrated. This is the 360 degrees that we were talking about. If I stretch it back out, notice that I can make changes, right? I can do whatever I want to this polygon. When I shrink it, it still shows the 360 degrees. Including making the polygon concave. So, he's putting this in as part of the theorem. It's part of the requirement, but it's not. Okay, it's not. 360 degrees is the sum no matter what. You just have to be sure that you're defining your terms correctly. And this also can illustrate that it works for polygons of all different sizes, for example, a quadrilateral. So I hope that this gives you an illustration of why these videos are not all that the media is leading you to believe. Those of us who are career mathematics educators, we have so much better ways of explaining the mathematics so it makes sense and so students can actually understand it. And we have so many better models to illustrate this than just the equivalent of drawing on a board. Thank you so much for listening.